So these turned out good. It's probably creased on the underside, but I don't think that matters as much. Are you?
Yes, I am.
I feel like one of those not cool kids. You're gonna cut that, right? So we'll just cut some dog bones, I guess. In order to get an idea of the strength of the fiberglass material, we needed to create dog bones, a standard shape used in the tensile stress testing. And these dog bones were used to test the elasticity, the modulus of elasticity, and to find the ultimate strength of the fiberglass and resin. This part of the video is demonstrating how we created the dog bone shapes out of our fiberglass material. Not the worst dog bone in the world.
Not the worst. Not the best either.
With using the UTM and the extensometer, we were able to gather data that we could put into an Excel sheet, graph, and find the modulus of elasticity, yield strength, and ultimate strength of the fiberglass. When the fiberglass dog bones break, we have reached the ultimate strength, and the test was concluded. By combining the empirical data from the fiberglass and the foam, we should be able to hypothesize the material data for a combined foam and fiberglass resin test sample. After tensile testing the dog bones, we were able to move on to testing the deflection of several beams. For the plain foam beam, we decided that the load cells from the UTM would not be accurate enough, so we had to find a different way to measure the deflection and apply and measure the load. We ended up using a cantilever beam setup. So we ended up hanging weights from the plain foam beam. We slowly added the weights to the end of the beam until the ultimate strength and failure of the beam occurred. We recorded data at after each weight interval was added. After the used dial indicator, we realized that our weight method and our method of measurement was not adequate for the plain foam because of how much it deflected. For the second foam test, we used a different measurement method. We used a tape measure, as well as making a longer beam so that it would take less weight to deflect the beam to failure. The composite beams, both the sandwich beam, which was the foam in the center, and fiberglass on the outside edges, and the 3-layer fiberglass, which had fiberglass on the outside edges as well as a piece of fiberglass through the center. To construct those beams, we basically wrapped the foam in packing tape as a barrier to protect it from the fiberglass resin. Once we had a complete barrier around the foam is when we applied the resin and fiberglass. And then we put plastic film over it and compressed them with weight to ensure that there weren't any big air bubbles in between the fiberglass and the foam. So to test the composite beams, we used the same cantilever beam setup. However, to add weight and measure the deflection, we needed to change our methods again. We used the tensile test machine to apply a steady load. We made a scale basically that had an indicator at each 1/10 of an inch, and then we used a pull scale, a pull or push scale basically, to measure the pounds force that we were applying to the end of the beam. Using the same methods of measurement as the sandwich beam, we tested the 3-layer composite beam. When doing this test, we found that the capacity of our machine to deflect the beam reached its limit, although we realized that that is all extraneous data, because with the fiberglass in the center of the beam, from our data you can tell that it almost immediately separated from the foam. And we think this is because with the fiberglass in the center of the beam, it was seeing the most shear, as the maximum shear in a beam is at the neutral axis. So with how much, even with the sandwich beam that separated the fiberglass that was at the very outer edges, that was seeing very little of the total shear in the beam. So it was unsurprising that the beam with fiberglass in the neutral axis failed almost immediately, as it was seeing a lot more of the shear. We think we got enough data between the normal foam test and the sandwich composite beam, which was just the 2 layers of fiberglass on the outer edges of the foam, to conclude that for a given load, the composite beam certainly helped to prevent deflection as compared to the normal foam beam. The 3-layer beam was pretty much a failure since it sheared almost immediately. So, like you've heard a few times in the video, what went wrong is that the delamination between the fiberglass and the foam. So that would effectively be a lack of adhesion between the layers of the composite beam that allowed shear flow, the internal shear in the beam, to separate the two components. If we could do it again, how would we do it differently? I think we would actually construct multiple beams out of different adhesives and fiberglass resins to try to find a beam that actually could withstand a decent amount of shear force. None of the composite beams failed due to bending stresses. They all failed due to the shear.